Hello everyone, my name is Tianyi Ouyang. I'm from University of California, Riverside in CH Louis Group. Today my talk is about enhancing resonant second harmonic generation in bilayer WSe2 by layer-dependent exciton resonance effect. So first let me briefly introduce the second harmonic generation in monolayer transition metal tetrachlorogenide. So for example, like a WSe2 monolayer. So in this kind of system, if we shine a light with a frequency omega, and we can detect 2 omega light. So this is because the nonlinear optical response happening in the system. And in monolayer TMD, like WSe2, it has strong second harmonic generation. Now we consider another monolayer, but this time we rotate it by 180 degrees, and we use different color to represent it. So we can also shine a frequency omega light to this monolayer, and it also has 2 omega light SHG response. But this time we stack two monolayers with 2H stacking configuration, and we're going to see that the SHG responses of two monolayers have a perfectly destructive interference. So finally, you're going to get zero SHG output. So this is actually the result. Like there will be no SHG in 2H bilayer TMD system. In previous study, people try to break this kind of symmetry and enhance SHG in 2H bilayer TMDs. So the way that they used like this kind of reference, they apply out-of-plane electric field. We also reproduced this kind of result. So we fabricated bilayer devices like this way. Is a dual gated device with few layer graphene as top and bottom gates, as well as contact, and also BN encapsulation. And this is the optic image of our device. So the electric field is applied like this way. So it's from layer 1 to layer 2, and the layer degeneracy will be broken by this kind of electric field. And SHG responses of each layer will be a little bit different. So in this kind of configuration, that the perfectly destructive interference will be damaged a little bit, and you are going to see a finite superposition result. So this is actually our experimental data. So we can see that at zero electric field, the SHG signal is actually negligible. And at finite electric field, the signal is also finite. But there is a problem of this kind of way to enhance SHG in 2H bilayer TMD system is that the SHG is not efficient. And we need to apply a very large electric field to enhance this kind of SHG signal in the system. So we need to figure out a way to enhance this process. And here comes to our idea. So we try to apply layer imbalance charges. So the main idea is like this. The same configuration here, but we apply charges without any electric field first. And then we apply a tiny electric field. So this small electric field can still break the layer degeneracy, but our aim is try to accumulate charges in one layer. So after we apply the electric field, the charges will move to one of the layer. And then the second step is that we apply the resonance effect. So we try to tune the wavelengths of the incident light and let the 2 omega resonate with exciton signal. So we know that in the TMD system, the exciton is a well-pronounced optical response, and for each layer they have their own intra-layer exciton responses. And here we try to let the 2 omega resonate with the exciton, and in layer 1 the exciton signal is preserved, so it can have resonance effect. But in layer 2 the charges are accumulated, so the exciton signal is suppressed, as we know that the exciton are formed to exciton polarons. So the resonant effect will be suppressed a lot. Finally, for the superposition of the two SHG responsives from two layers will be very different. And the perfectly destructive interference will be destroyed a lot. So the total SHG in 2H bilayer system will be much enhanced. So this is actually our idea. And then let me briefly introduce our experimental data and the main result. So we start from the reflectance contrast spectrum. So we need to use this way to define that the charges are really accumulated on one layer. So this is actually the second derivative of our reflectance contrast spectra. At the finite electric field, the y-axis is charge density. So we can clearly see that there are different charge doping regime. For example, this red regime corresponding to both layers are intrinsic. So here, there's no any charge doping. And then in the second doping regime, marked by blue, is actually one layer has holes, the other layer is still intrinsic. And finally, the last regime, marked by green, is actually both layers are doped by holes. So this is actually very clear in the reflectance contrast spectral measurement. And then we check the SHG in three different doping regimes. So we apply scanning SHG across resonances. So here comes to our result. So we can see that without any resonance, the signal is quite low, but when we try to tune the wavelengths to the exciton resonance region, and we can see the SHG gets much enhanced. And also in three different doping regimes, in the blue region, the SHG gets enhanced the most. So we can say that the SHG gets much enhanced when only one layer has holes. And then later we try to figure out we try to measure more reflectance contrast maps at different electric fields. So this is actually the zero electric field data. The upper panel shows band alignment schematics, and the lower panel shows the result of our reflectance contrast data, and then followed by a finite electric field with positive and negative electric field results, and a larger finite electric field result. So we use different symbols to mark the ages of the different doping regimes, like a circle, triangle, and square. And we can connect those same symbols by dashed lines. And we can clearly see that in the red region, it means that both layers are there's no charges. It means that both layers are intrinsic, and then followed by two blue regions that only one layer has holes. And the last region is marked by green, that both layers have both layers are doped by holes. So now it's very easy for us to extract the data from the reflectance contrast spectra and summarize in this diagram. So in this diagram, the y-axis is charge density and x-axis is electric field, and different doping regimes are marked by different color. So all the data are extracted from reflectance contrast for now, and we also have another measurement result, which is about SHG intensity phase diagram. And it's very easy for us to overlap these two diagrams, and we can see that in a one layer doped configuration, the SHG gets most enhanced. So this is actually the main result of our experiment. And finally is the summary. So first we performed reflectance contrast spectral and exciton resonance SHG measurement on our dual gated bilayer WSe2 device. And we actually observed SHG is most enhanced when only one layer is doped by holes. And the physical mechanism behind this phenomenon is actually The layer imbalance charge can break the inversion symmetry more than pure electric field effect. And our work is published on this nanolater paper. And that's all. Thank you very much.